Bismillahirrahmanirrahim. Assalamualaikum. How are you everyone? So we are going to continue with solving problems from chapter number 4, and we reached to 420, problem 420. I know we are taking some time solving problems, but this is the way how we can understand things. So it's not enough to just to explain to you the concepts in the chapter or the problems, the equations that we use for a flow of a liquid through a tank, or a flow of a liquid through a hole, or flow of a liquid through a pipe, or flow of a gas through a tank, or for flashing. So that is not enough just to know the equations. You need to solve problems. So getting into the problem here. So 420 says that we have an accident, right? Okay, an accident mitigation, part of the risk procedure is called emergency material transfer. So what is this emergency material transfer? Transferring material from one place to another as an emergency, in which the material is transported away from the accident site before it becomes involved. So there's a problem, there's dangers on that storage tank. We know we need to take everything from that storage tank to another storage tank. So we plan on mitigating a crude oil tank fire scenario, okay, by pumping the tank empty in 1 hour time. So in 1 hour before the fire gets to this crude oil storage tank, we want to shift it to another crude oil tank. So the crude oil storage tank is 30 meters in diameter, and we want to take it to another tank, which is about, we'll see how far is that. So the first crude oil storage tank is 30 meters in diameter. Imagine 30 meters diameters, that big, and it's a 9 meters level. So it's a big tank. The transfer will be accomplished by pumping the crude oil through a 200 millimeter internal diameter. So we have a 200 millimeter internal diameter steel pipe, and we want to take it to another tank which is 40 meters in diameter. So it's bigger, and it's 10 meters high, not only 9 meters high. So the pipeline represents 50 meters of equivalent pipe. So it's about 50 meters, it should travel 50 meters to reach to the other tank. Okay, so just to look at that, before we understand the whole problem. So I have a tank here, and I need to pipe, I need to take this to a long distance here to another tank, right? So there's a pump here, and I need to shift it to another tank which is 40 meters in diameter, right? It's 40 meters in diameter, and the other one was just 30 meters in diameter, right? 30 meters in diameter, and I want to take all this amount that is sitting here to the other side, and this is 10 meters. And of course, to shift it, all of it, I mean, if this was 9 meter high, it will be in a less height here because this one is wider, right? So we need to know how to fill in this diameter, how high it was going to be. So what is the question? The question is telling me that what is the WS? What is the horsepower that I need? What is the strength of that pump? To pump what? To pump all of my liquid here to this tank here. So considering that all of it going to be pumped here, so that's like 0.1 here, where it's going to be empty, and then 0.2 where it's going to be filled. So delta Z, in this case, delta Z, so this is like delta Z, right? Delta Z. From my mechanical engineering balance, where for 0.1 till about 0.2, and my 0.2, actually I should put my 0.2 here, because it will not reach to that level. Why? Because it's wider, right? So it will only reach to this level here. Okay, so that is the delta Z. What did I start solving? No, I'm just trying to understand. Okay, so the transfer will be accomplished through a 200 millimeter and it's 50 meters. So I need to write that. So I have here, if I would say, I put that in red. So that is about 50 meters. and I have the diameter, internal diameter in this case for this pipe. Okay, so this pipe, the internal diameter for it is 200 millimeters. So 200 millimeter, which is about 0.2 meters, right? 0.2 meters. So this is what I have. The first question is asking me estimate the minimum size pump size. So I want what is the horsepower of that pump to empty everything in 1 hour. Okay, so I want to empty this. I want to empty tank 1 in 1 hour. In 1 hour. Okay, so what is the horsepower to empty in 1 hour? Assuming a pump efficiency of 80%. So that is good for a pump efficiency. So I'm talking about the good pump here. So we need to consider that it's operating on 80% efficiency. Because if it's on old pump, then that means you need a stronger pump. You need a higher horsepower depending on how much you want to achieve of that horsepower. Okay, so what do we have? We are going to apply. You're going to apply a mechanical engineering balance, because what do we want to know? We want to know the WS. So our mechanical engineering balance, mechanical energy balance, okay, is delta P over rho, plus delta U square over 2GC plus G over GC into delta Z plus F, right, is equal to minus WS over M, the mass flow rate, right? So what do I have here? Both of them are open to atmosphere, right? Both of them are open to atmosphere, and in this case I'm going to say delta P is equal to 0. And if you look at it like for the velocity, this is like pumping. If I'm considering that this is the velocity here and this is the velocity here, so both of these velocities is like really low, both of them, so they are 0. It's like both of them are open to atmosphere. Here the velocity is not moving much, it's not moving much here. So delta U is going to be 0 as well. So beautiful, things are becoming really simple here. So what else do I have? Delta Z here, I don't know what's delta Z. I know that when it empties, when it's going to empty up here, is going to be a certain distance here. To find this distance, I'm going to say that the whole volume here is going to go here. So if I equate this volume to this volume, I'm going to find the delta Z. Okay, so I can find delta Z by equating two volumes. So I'm going to write this. So I can find that by equating V1 is equal to V2. What about F? Well, F is knowing the friction factor. So what I have here is the friction factor, because I need to consider that this pumping will also need to go over the friction factor. So it's not only this amount, so the friction factor. So I have a pipe here. Okay, so I have a pipe. So the only thing that I have as a pipe here, I'm going to consider this as a K pipe. Okay, and I'm going to say here that I need to find the K pipe, where I can find that's the KF, right? The 4LD over whatever, 4FL over D, right? So the K pipe, which is 4FL over D, and to get F, we need the Reynolds number, which is rho dV over mu. Okay, rho du. Okay, I'm used to the V because that was stuck in my head when I was a student. So for velocity here, we are using U. So it's rho du over mu. So we need all that information. That's easy. But we need U, right? And how to get U? Use the velocity. So if I have the volumetric flow rate, and I do have the volume, right? I do have the volume, and I need to finish everything in 1 hour. So talking about a volume in 1 hour, so I would say that if I have the volume that I need to finish in 1 hour, I have the volumetric flow rate, and the volumetric flow rate, I just need to multiply this by density. And if I multiply this by density, I'm going to get the mass flow rate. Oh, hold on, why should I do this? I don't need the mass flow rate. Well, if I can't get that information, right? The volume that I need to finish in 1 hour, I multiply by density, I'll get the mass flow rate. So I got it. So, but what about here? So I have the volumetric flow rate. I just need to get the U, which means I just divide by area. So I divide by area, to get like this feet cube per hour divided by feet cube to get how much per hour. Then I can have it in seconds, how much, for example, feet per second. So I think so I have a good shape now of what I'm trying to solve here. So one by one I'm going to get delta Z, and then I'm going to get K pipe. Of course, if I need to get this F, I need the Reynolds number, and of course I forgot I need also E over D, the roughness factor. So if I get this, I can get that, and of course to get this U, I need this information here, substitute U, get Reynolds, E over D, get F, and if I get F, I can get K pipe, and that's good, right? So I think so we are ready to solve the problem. So let's go on. So the first thing that I'm going to consider, I'm going to find delta Z. And to find delta Z, I need to equate the two volumes. Talking about volume 1, the volume 1, it was 9 meters, it's pi d squared over 4, right? Multiplied by L. And in this case, it's pi d, the d was 30 meters, 30 squared over 4. And multiplied by L, which is 9 meters, the height, and in this case it will be 6.36 into 10 to the power 3 meter cube. Okay, and if we go to the second one, the second volume of the second tank is pi d squared over 4 into L. So what do I have here? I have pi d squared, pi 40 squared over 4 multiplied by L. Okay, so here I don't know what's the height, and this is where I'm going to get the delta Z, right? I don't know what's the height here. So if I equate V1 is equal to V2, this will be 6.36 into 10 to the power 3 is equal to pi into 40 squared divided by 4 multiplied by L. And here I'm going to get my L value. Okay, I'm going to get my L value. And if you want just to calculate this was area 3.14. It was 3.14 into 10 to the power minus 2 L. So I'm going to substitute this here and say this is equal to 3.14 into 10 to the power minus 2 L, and L is equal to 5.06 meters. Okay, 5.06 meters. So that is my delta Z, right? That is my delta Z here. So delta Z is equal to 5.06 meters. Great. So I have my delta Z here. That's delta Z is equal to 5.06 meters. So what else? Now what I need to calculate, I said that I don't have the velocity. So to calculate velocity, okay, so to calculate the velocity, what I need here is to say that velocity is the volumetric flow rate. We said that is the volumetric flow rate, right? And we know that the volumetric flow rate is the volume given to us that should be taken out within 1 hour. Okay, so that much meter cube that should be taken out in 1 hour. If I want to put this in seconds, this amount I need to finish in that seconds. And if I divide this by the area of the second tank, which is 3.14 into 10 to the power minus 2 meters squared, this will give me the velocity that my pump should pump with, right? So it's equal to 56.26 meters per second. So now I'm saying that my pump should pump this velocity here, right? It should pump this velocity here. Okay, and just to continue on, if you go up, just to remember, so what I have found here, I have found the velocity. I have found the velocity. Why did I find the velocity? It's for two reasons. It's good for the mass flow rate, and it's also important to find the friction factor, right? The Reynolds number and E. So I'm going to find the Reynolds number, E over D, so I can find the friction factor. Okay, so this is what I'm trying to do here. So I have now this U, and just to calculate the Reynolds number, as I said, D rho U over mu, and this is equal to 0.2 meters, which is the diameter of that pipe, into 928 kilogram per meter cube into 56.26 meters per second, divided by mu, which was given to us, which is 0.004, and if that is going to be equal to 2.61 into, okay, again 2.61 into 10 to the power 6. And if you can see here, this is definitely turbulent. Okay, that is really turbulent. And here, instead of using the figure, because it is fully turbulent, if I would say, like this is like fully turbulent, okay, fully turbulent, I'm going to use the equation, and this equation is a simpler equation that is already given to us, which is 1 over square root of f is equal to 4 log 3.7 to the power d over e. I think, you know, to multiply by d over e. Okay, so that is the equation. So I need e over d, of course, and e over d. If I'm going to calculate this, the roughness factor, you're going to find the roughness factor, which is 0.046 from the table. We already have steel pipe, over the diameter, which is 200 millimeters, right? Millimeters here, which is 0.2 meters. That is equal to 0.00023. And if I substitute this to calculate the friction factor, so 1 over the friction factor under the square root into 4 log 3.7 into d over e, which means that's like it's a it's a division here, and you're going to find that f is equal to 3.53 into 10 to the power minus 3. So we found the fanning friction factor, and as I said that we need the fanning friction factor so that we can calculate the f term here. Great. So what else do we have? I think so we have all our equation here. All what we need is to do our substitution. So again, what was our problem? It was delta P over rho plus that U square over 2GC plus G over GC into delta Z plus F is equal to minus WS over mass flow rate. Oh, did I calculate the mass flow rate? I forgot to do this, but we have already U and we can get the mass flow rate. Don't worry about it now. So that was 0, that was 0, and we got delta Z is 5.06. So just substituting, so this is like 9.8, which is the G term, over 1, of course, for S units, into 5.06 plus F. F is the friction factor, which is 2FL, is the friction factor, which is, oh my god, it's 2FL U square over GCD, right? So that is 2FL U square, because you're substituting the KF term as well. So this is the equation here. So that is 2 into 3.53 into 10 to the power minus 3, that is the F, into L, which is 50 meters, into the U term square, which is 56.3 square. What else do I have? Over GC, in this case, it's like 1 for SI units, into the diameter, which is 0.2, and all that is equal to minus WS over the mass flow rate. Okay, so let's keep the mass flow rate now. Hold on, we are going to come to it in a moment. Okay, so that is like 49.6 joules per kilogram that I have here, plus 5595, that is joules per kilogram, is equal to minus WS over M. The thing that I did not finish yet, but I can already realize that this is very small in comparison. So see, you can see that like this is negligible in that sense. But we are going to continue on. But it just shows you that how are the other terms are much more higher now in comparison to this term here. Okay, so just to continue, this is just an information here. So now to calculate the mass flow rate, the mass flow rate is rho U over into A, and that this is equal to 928 into 56.3 into the A, which was 3.14 into 10 to the power minus 2, and the answer is going to be 1641 kilograms per second. Okay, so I have my value for the mass flow rate, and if you calculate it, you're going to find that WS is equal to 9.26 into 10 to the power 6 joules per second, and of course you know that like 1 horsepower is equal to 745.7 horsepower, okay, joules per second. So to do this conversion, I'm going to have the answer is going to be about 1.2 into 10 to the power 4 1 to the power 4 horsepower. And considering that it is 80%, right, 80% efficiency, that means I need a stronger pump, and that will be about 15,000, oh, imagine, 15,500 horsepower. What a pump, what a pump. That is a really very big pump. And imagine, so this is really not possible. That is a huge pump, and it's not possible. It's just, let me put that in red. That is a really huge pump, okay? That is a really huge pump. Oh my God. So that is not possible. So if I want to put it possible, let me see my second part of the question. So the second part of the question is telling me, now, okay, you're saying it's not possible. I'm going to bring you a 100 horsepower pump, which is also 80% efficient. How long will it take to empty the tank? Okay, so I'm telling you what is the horsepower now. So again, if you're going to put the question here, so it's telling me that if WS is equal to 100 horsepower, okay, now it wants me to calculate time, and the time is simply saying that I want that volume, I want to finish up that volume over, of course, the volumetric flow rate. I need to calculate the volumetric flow rate, in which I can get this volumetric flow rate from the m dot, all right? If you just take m dot and multiply it by area, the area of that hole of that pipeline, right? I'm going to get the volumetric flow rate, and I already know the volume. So what I need to calculate here is the m dot. The whole story is all now to calculate the m dot. So is the other way around of calculation. And again, if you put your equation delta P over rho plus delta U square over 2GC plus G over GC into delta Z, that's the mechanical energy balance, plus F is equal to minus WS over m dot. And in this case, we already said that this is 0 and this is 0, right? And now here we already said that this is negligible, right? So that just to make my life easy, I'm going to just get it out of my sight. And getting it out of my sight means that I'm going to have the equation will be something smaller, and it will be just F is equal to minus WS over m dot. What I want here is the m dot, right? What I want here is the m dot, so that will be minus WS over F. And the whole story about m dot is all about the U term, right? The U term is the key, is the velocity. I mean, is the key of all of this, the solution of that. So to get my U term, I'm just going to do my substitutions here, and this is going to be m dot. Okay, let me put them here. So m dot is rho into U into the area, right? And my area is pi d squared over 4, so I'm going to just do everything in one go, is equal to minus WS over F. And what is F in this case? Okay, my F in this case, if you can remember, it is 2. Oh my God, it's not always to remember this. So it's 2FL U square, 2FL u square over gc into the diameter of that. So you can see here I have u and I have u here and I already have the horsepower, so I have only u as a term that I need to calculate. Oh my god, I also have the fanning friction factor, and this is where we need the assumption. We need to do this kind of assumption. So that would be u cubed minus 2 ws, I already have ws, gc over rho pi dfl. So what I'm going to do here, this is going to the story of what I need to do. So I just need to substitute. Just to remember, so what is ws? Ws is 100 horsepower, but we know this 100 horsepower is 0.8 efficiency, and I need to what they said, to convert that horsepower into joules per second, okay, into joules per second, which is about to be let me say about 6, okay, 6 into 10 to the power 4 joules per second. It's about 6 into 10 to the power 4 joules per second. So what you need to do here, if you substitute everything, all the other values here, u cube is going to be equal to, should I show you the whole terms? Well, let me do that, that's fine. Into gc, which is it's okay, SI units, so that will be 1 divided by rho 928 into pi 3.14 into d, which is 0.2 meters, into the f term, which I don't know, f, which is 50. So this u cube is going to be equal to 4.095 over f. So what do you need to do here? If you can recall, I guess u. Why? Because I cannot find f. I cannot find f except if I have the Reynolds number, but I don't have u. How I can get it? How can I get that? So what I need to do, I already have e over d, so I need to get u, and by guessing u, I will get the Reynolds number, and then I will get the f number, and then I'm going to calculate, right? I'm going to calculate the new u, the new u, right? The new u, depending on which equation from this equation. And then I'm going to say, well, is my new u minus the old u, are they the same or not? If they are not the same, so I'm going to calculate again this repetition, the Reynolds number, and then getting the f term, and then of course getting the new second u, right? The second iteration. So you're going to get an iteration process here, and doing this iteration, you're going to find out that if you put a guess of u of about 11.1, and you're going to get something like that. I'm going to start doing this thing here. So that will be something like a fanning friction factor of 0.003, right, 11.1, and then you're going to calculate the Reynolds number. You can do it the other way around, by the way, okay? You can do it by the way in which you calculate you can assume f number, the f, to get just any f, and then by putting an f term, okay, you're going to get u, and from u you're going to get Reynolds number, and then you're going to calculate the f, the new f. So you can do it also the other way around, and this is what what is done here, and then you're going to get the f calculated, okay? So we are doing it the other way around. Doing it here or there is all going to be the same. So in this case we are assuming f is equal to 0.003, okay? So to continue with that, this is my table that I have here, and then calculating with the new f. My new f was 0.0062, taking an average value of like the new f or the old f. You can do this, by the way. let me see. So getting the new F calculated, I can get the new Reynolds number. Okay, so let's do that. So doing your iteration here, and it looks like it's very fast iteration because we already got the F calculated, in which if you substitute 0.0062, you're going to get this 8.71, and that will be 4.05 into 10 to the power 5, and then you're going to get your new F calculator, which is 0.0062. Oh my god, that looks exactly to the value that we have substituted here, and based on this we are going to say that this is my U, right, and this is my the fanning friction factor. Now considering that I have everything ready, so all what I need to do now is to calculate the Q, and as we already said that if you get the volumetric flow rate, and that was my value, I get the volumetric flow rate, and this will be 985 meter cube per hour. Now that is volumetric flow rate. To get the time, we said to get the time, which is the volume that I have divided by the volumetric flow rate, right? And in this case, when I did this, I found out that it will take about 6.45 hours. Is this good enough? I think so. To talk honestly, about 7 hours is a lot. If you have a fire, and a 7-hour emergency is not good. It's not good. And because it's not good, you need another plan, okay? You need another plan. You need another plan. It could be a smaller storage, right? A smaller storage. We need another plan. It doesn't work, okay? It's not working. So that is the whole part of 420. I know that was a bit long question, but it was very interesting to look at a real application here. Great. So talking about the other rest of the problems, 421, 422, I'm going to keep that to you as an assignment, and I'm going to write everything for you as an assignment later. And they are very nice problems. We already had solved something very similar to 421, 422, 424. So what we are going to go through, we are going to go now, that's 421, okay? So storage tank with water, and the tank's 3 meter and 6 meter high. So what's the final liquid level? It's interesting. 422, again, you're having a 3 centimeter pipe that was broken, and it has nitrogen. What's the maximum gas flow rate? This is like about straightforward. And then if you go to 424, I'll think about 424 if I will give that to you as part of the assignment or not. So let's go down there, and I want to go to 438. What I have skipped was the part that I was talking about the flow of gas in a pipe, and we did not take that part. So this is why I skipped all the problems. There's also something related to the dike. We did not cover that as well. It's not that it is difficult, but I just want you to concentrate on at least something that you can grasp now, rather than taking many things and you don't grasp anything, okay? So that's the idea. Okay, so what do we have here? We have 438. So 438 says liquid chlorine is supplied to a process from a regulated pressure source at 20 bars gauge pressure through 300 meters of horizontal new steel pipe. So it's 300 meters long, and then side diameter is 0.02 meters. The pressure is 1 atmospheric. The temperature is 30 degrees centigrade. So if the pipe breaks off at the regulated source, that is from the source. That is from the source where we have a 0.02 inch diameter. Estimate the flow rate through the leak in kilograms per second. and because it's like a source, I don't know, we could consider this as a whole of that amount of 0.02. It's like the whole area is opening. So what do I have here is like this is 438, and what do I have here is like I have a pipe, and that is 20 bars gauge, and it's got broken in this side here, right? It's got broken from here, and so this is broken, and that is considered the diameter, which is 0.02 meters. So that is the whole of that broken thing that I have here. Okay, and that is within 300 meters long, and what else do I have? So these are the information that I have. So I have chlorine, and if I want to solve this problem, I think so we can say that it's like a hole in a pipe. So my equation, I'm going to apply like a liquid in a hole, which is AC naught 2 rho GC into PG, and it tells me, of course, it wants the QM, which is the flow rate. That is the requirement of the question, and I'm just going to start substituting. Okay, I'm going to just start substituting. So I need the area. What is the area? Area is pi d squared over 4, and of course this is the area of the hole. So here the area of the hole, I'm considering it that is the internal diameter. So pi d squared over 4, and this is equal to 3.14 into 10 to the power minus 4 meters square. And I'm going to for C naught, I'm going to say this is sharp edged, so I'm going to say C naught is equal to 0.61. What else do I need? I have the PG already is given to us. Let me look. So the ambient pressure is equal to 1 atmospheric pressure, and I have the ambient temperature is 30 degrees centigrade, and of course I have the PG here, which is 20 bars. Okay, so that's the power gauge. Okay, so PG is equal to 20 bars. I already have this, so I think I'm going to substitute. So QM is equal to now A, which is 3.14 into 10 to the power minus 4 into C naught. C naught is 0.61 into the square root of 2 rho, and the density of chlorine is 1380 kilogram per meter cube. Okay, so that is the density of chlorine multiplied by a GC. I'm taking SI units, so it's 1 here, into PG, which is 20 bar gauge. So I need to change that into newtons. So that is like 10 to the power 5 Newton per meter square Pascal over bar. So I think so everything is there. The answer is going to be 14.2 kilograms per second. Okay, so that was the first part. This is the amount that I'm going to have getting out. Imagine that this amount is not small. I'm talking about 14 kilograms per second. This is crazy. If you go and see, if you arrive this within half an hour, or my god, we multiply by 30 minutes. Oh my god, that's in seconds as well. So I'm talking about like 1 minute, which is like 60 seconds. I'm talking about, if I talk about 1.5 minutes, about 90 or 100 seconds, you're talking about 1,420 kilograms. That is a big amount. So you just imagine of how big is that. Now, to consider that, the second part where it says that if the pipe breaks off at the end of 300 meters length, okay? So it breaks out at the end of the 300 meters. So I'm talking about it's breaking up by the end of that here. So it breaks up here. Well, breaks up here, we need to consider what? There's a lot of, there's a delta P, okay? There's a pressure. So the pressure here is different. The pressure at this point will be different, okay? So to consider the difference in pressure here, so we need to do the mechanical and energy balance, and during our mechanical energy balance here, so we have the delta P over rho, the delta P over rho plus delta u square over 2gc plus g over gc into delta z plus f is equal to w minus ws over m. I think so I forgot one term here, so that is I think everything is correct here. So what do I have here? I have that it's a pipe, like horizontal pipe, so delta z is equal to 0. So what else do I have? I have no kind of a shaft work, so that is equal to 0. So I have a friction factor here that I need to calculate. What about the u? U, I would consider was like the same velocity getting in and getting out. So it's like entering and exiting with a certain with the speed. It's liquid. It's not pressurized. I mean, it's liquid. That's why it's incompressible. I don't have a pump on one side that I want to see. So delta u is equal to 0. So what I have here is my system will be shortened down to delta p over u is equal to minus f, which is minus 2f L u square over GCD. Okay, and if I want to solve for to know how much delta p I do have here, well, I will need all the values here. So what I have here, again, the same story. I need to find f and I need to find u. Okay, I need to find f. The thing is that, like, f is what? Like f, to find f, what do I need? I need the Reynolds number, right? And E over D. To get f, let me put the arrow on the other side. Okay, so I need these two to get f. And if I want the Reynolds number, I need u. Okay, so how to calculate u? I don't have u. So, and this is the whole story again, where you need to assume a u, get a Reynolds number, and so on. But if you look at that for a moment, actually, all what I want to get at the end is Qm, right? I want to get Qm. And to get Qm, what I need is the velocity multiplied by u, rho, into A. So this is what I need to get. So if I can get u, and I already have the density and area, I can get what's the mass flow rate at that broken end. But how to get u if I don't have delta p? We thought that we don't have delta p, but actually delta p is broken at one end. So we are talking about the P1 minus P2, which was entering at a 2 whatever it says. What was that number? It was 20 bar, right? It was 20 bar. Okay, so we can say that 20 bar at one side gauge, and the other side is like open to atmosphere, so that will be 20 bar. So we have delta p. We have delta p. And here for f, we have that is really turbulent flow. So maybe we have a way of how to calculate f as well. Of course, we still need some kind of numbers here to substitute. But if it is totally turbulent flow, and that is just an assumption that we are just by looking at the 20 bar, we are saying, well, 20 bar sounds like a really fully turbulent flow. And because it's a fully turbulent flow, we can use a simpler equation, and that simple equation for fully turbulent flow, the one that we had used before, it is 1 over square root of f is equal to 4 log 3.7 into d over e. And in this case, what we're trying to say is that we don't need to do the guess game, right? Why? Because there's no u here. There's no u here. And in this case, I'm going to calculate E and D, and then I'm going to get F, and then substitute F. I already have delta P. I'm going to calculate U. Okay, so that is the whole idea. So what we are going to do here, we are going to calculate F. So F is going to be, you need to do that by your own, is equal to 0.078, the square root of f is going to be 0.078, and f is going to be 0.0061. and by calculating F, now I can substitute in the equation, and this equation, I'm going to do that, I'll show it to you like that. So this equation is going to be, U is equal to square root of minus delta P into GC into D, right, divided by 2FL rho. And if you do this, you just need now to substitute, and you're going to find out, after substituting all the terms, I'm going to show you the substitution here. So that is my 20 bar, and just putting it in Newton per meter square, okay, and that is GC, which is 1 into 0.02 meters, the diameter, over 2F. F was found to be 0.0061, okay, 0.0061 into 300 meters into the density, which is 1380 kilogram per meter cube, and the answer is going to be equal to 2.81 meters per second. So my QM is going to be the density multiplied by the velocity multiplied by the area, okay, to be equal to 1.22 kilograms per second. And we can see that this number is lower than the number that we have obtained earlier. So why? Because it's at the other end, right? It's at the other end. So the answer was 14.2. Definitely that was high, but I'm talking now about the other end. The other end, it is 1.22 kilograms per second. So that was question 38. I think so I'm going to solve like one more problem, and that would be good enough to finish chapter 4. That would be good enough for chapter 4. And I think so I'm going to keep number 39 for you as an assignment. And we solved a pretty good many problems here, and we will keep some for you to solve. And you're going to have good questions, by the way, to solve here. So try to solve 39, and also try to solve problem number, let me see here, 39. 39 is a pretty long problem. Ooh, that will be really challenging for you. That will be challenging, but it's interesting. You're going to enjoy it. Okay, great. So I think so that's all. That's what we need to do. I think I have one question. I have in mind one question that I had planned to solve. Just give me a second. Okay, so the question that I forgot just to solve was 431, but I think so that is simple and straightforward, because we already solved many problems within the same concepts. What it says, just calculate the numbers of kilograms per year of ideal gas that can be transported through pipe sizes, assuming a gas velocity of 3 meters per second, a pressure of 689 kilopascal gauge, a temperature of 25 degrees, and a molecular of 44, and the diameter that we have, the inter diameter is 3 centimeters. So straightforward QM. We want to calculate QM. We are not talking about any leaks here. We are just talking about what is the flow rate, okay? And the flow rate is rho A into U, right? So that's the whole story. And here we are talking about gas. So we already said that we are not going to cover the part of the gas in the pipe, but just for the sake that you may need this at one time when you graduate, is that if you want to calculate the amount that goes within a pipe, how much is the amount that goes in a pipe? And we know that the gas, we want to calculate the amount. We know the gas flow is 3 meters per second. The pressure is 689 kilopascal gauge, and that is about 790 kilopascal if I would put it into P terms. And the reason you'll see that why I want to put it in P terms, that temperature is 25 degrees, which is about 298 Kelvin, and the molecular weight is 44. So all what I need to do is that just to say, well, Qm is equal to rho into U into A, right? That is the equation that I have. And to say what is U from the ideal gas law, you can know that rho is Pm over RT, okay? It's Pm over RT, and multiply by the velocity into the area, which is pi d squared over 4. Substituting, you'll get 790 into 44, the molecular weight, divided by the universal constant, which is 8.3143, into 298 Kelvin, into the velocity that was given to us to be 3 meters per second, and then the pi d squared over 4, and here the pi is 3.14, let me write everything, 3.14 into d squared over 4. So d squared over 4. I'm not going to substitute for d squared because for different d I'm going to get different answers, and I'm just going to put everything as a function of d. So that will be 1.042 into 10 to the power 9 d squared. Now for case 1, that if I have a diameter of 0.03 meters, I'm using a pipe of 0.03 meters. What will be my flow rate? My flow rate is going to be 9.38 into 10 to the power 5 kilograms. That would be 10 to the power 5 kilograms. And I need to put here the amount of time. So there's something that I did not include here. And actually here, I forgot to show you that we have multiplied here, because we want to see how much per year. So I'm multiplying here 3.154 into 10 to the power 7 seconds per year. In this case, I'm calculating how much amount per year, right? And so that was the equation that I have, was per year. Okay, so this is the amount I have here, kilograms, that I have per year, right? That is the amount per year. And if you have the diameter was 0.05 meters, the Qm was found to be 2.61 into 10 to the power 6, that is per year. And for C, part C, the diameter was given to us. If I use a 0.25 diameter, 0.25 meter diameter, what would be the Qm? It would be 6.52 into 10 to the power 7 kilograms per year. If I use a bigger diameter, which is 0.5 meters, I'm going to calculate the mass flow rate, and the mass flow rate is going to be 2.61 into 10 to the power 8 kilograms per year. Now the whole idea in this question is what? The whole idea, this is what I liked it, I wanted to show it to you, is that using a small diameter is much cheaper, right? And using a bigger one is more expensive, and a smaller one takes less space. This takes more space, even though that space is not always is not an issue. But what you want to see is that, well, just by looking at the amount actually is not that difference. I mean, from 0.03 to 0.05, we have some little difference, 9.38 to 2.61 to the power 6. So that is a very small amount. And even if you consider that from 0.03 meters to 0.25, which is about 10 times, right? 10 times bigger. And how much is it? How much is it bigger? Well, it takes a big amount here, but it is not that difference as well. It is about a difference. It's like 10 to the power 7 per year. But we're talking about 10 to the power 7. And the whole idea is that I'm just trying to show you that is it worth it to go for bigger amount, bigger diameter to transport with that big amount? Is that amount big enough, good enough? So that is the whole idea. That is the comment that we have here for this question. So what is the comment here? The comment I have here is that you can transport big amounts. You can transport big amounts with a small pipe. And that is a very important conclusion, because you're saying that I don't need large pipes, and they are much more expensive, and sometimes it's like easier to use small pipes and replace them. So that is a good conclusion that we can get to. If you want to solve something similar to that, actually problem 431 is exactly the same. It's just that it is repeated. It's repeated. So this is all what we have for our problems. We have covered all the problems, the possible problems that we want to cover in this course. So hope all the best. We had done a good job. Give yourself a clap. Be happy. Be happy. It looks like this person's not happy. Okay, so try to be happy. Okay, that's better. So try to be happy. Enjoy your time. We had done a good job solving all the problems. Thank you very much. All the best. Maassalama.